In this video, we're going to look at a couple examples of solving equations that have complex solutions. The first example we have here is if we have x squared plus 6x plus 10 is equal to 0. Now, normally we would start out with this problem and we would say, well, can we factor this expression? And we would try to factor x times x is x squared, and then 10 would be 1 times 10 or 2 times 5. And we find out if we try 1 and 10, that's not going to give us the 6x in the middle. Or if we come back and we try 2 times 5, we're not going to get the 6x. So here, we're not able to factor this trinomial. And if you go to your calculator and you were to graph the trinomial, the graph of this is going to look something like this, where if we go from negative 10 to 10 on the x, and negative 10 to 10 on the y. So if you go to zoom standard with your calculator, the graph of this is going to be a parabola that opens up something like this here. And we can clearly tell the graph never crosses the x-axis. So what that tells us is this equation is never equal to 0 when we think of the real number system. Now we're looking at the complex solutions. So we're looking at where does this equation equal 0, looking at not just the real numbers, but the complex zeros. And the only way that we can really go about finding this is by using our quadratic formula. So we're going to use x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Now, when we look at this using the formula, it may be helpful if you want to go up here and write, we have our trinomial. We know that here a equals 1, that's the coefficient of x squared. B is equal to 6, that's the coefficient of the x. And c is equal to 10, that is our constant term. So if we plug these values into the formula, we have x equals a negative b, so that's a negative 6, plus or minus the square root of negative 6 squared minus 4 times 1 times 10. And all of this is divided by 2 times a, which is 1. So at this point, we could go to the calculator and simply enter all of this in. And we would end up with a negative 6 plus or minus. And this is going to go to negative 6 squared is 36. So this is going to be 36. And then we have minus 4 times 1 times 10, which is 40 all over 2. So then we have a negative 6 plus or minus the square root of 36 minus 40 is a negative 4. So this is where we, in the past, would have said, well, if we had a square root of a negative number, we would say there's no real solution, which means there's no real 0. And we can tell from the graph it never crosses the x-axis. Now we're looking at the complex 0, so now we know we can take the square root of the negative 4. Well, the square root of 4 is 2. The square root of a negative is I. So we're left with negative 6 plus or minus 2i divided by 2. And once again here, we want to rewrite this so that we divide each piece by 2. And then we can say x is equal to a negative 6 divided by 2, which is a negative 3, plus or minus 2 divided by 2 is 1, so we're left with 1i. Now keep in mind, when we have a solution, a real 0 solution here, notice we have two answers, negative 3 plus or minus I. We have one answer here that is negative 3 plus I, and the other one is negative 3 minus I. Now what do we notice here? Your answers turn out to be conjugate pairs. So anytime that you have complex zeros, your complex zeros will always occur as conjugate pairs. So that tells us you're always going to have an even number of complex zeros. So if you have a -3 plus I, then a -3 minus I is also going to be a 0. They're always going to occur as conjugate pairs. All right, so let's look at another example. And this example here, once again, you may want to actually pause the video and see if you can work this out. We have 4.5x squared minus 3x plus 12 equals 0. And once again, we want to use the quadratic formula, so we're going to have a negative b plus or minus square root of b squared minus 4ac, and the whole thing is divided by 2a. And once again, if it's helpful, you may want to actually label your a value. A is equal to the coefficient of x squared, which is 4.5. And be careful here, b is the coefficient of x. It's not 3, but it's a -3. And of course, our c value is 12. So if we substitute in, we have a negative b, so that's a negative 3 plus or minus the square root of -3 squared minus 4 times 4.5 times 12. And again, all of this is over 2 times 4.5. So if we go to simplify, -3, so that makes it a +3 plus or minus the square root of -3 squared, so that becomes a +9, minus 4 times 4.5 times 12 is equal to 216, and 2 times 4.5 on the bottom becomes 9. So then we're left with x equals 3 plus or minus the square root of 9 minus 216. That's going to be a negative 207 divided by 9. All right, now we want to simplify this as much as we can. And again, I'm not terribly hung up on simplifying the square root, but if we do that here, we could think of the negative as a -1. Can we simplify 207? Is there a perfect square in 207? So this is where you could start and you could use your calculator and you could say, well, 207, and we could divide that by the first perfect square. Well, 2 squared is 4, so if we take 207, divide that by 4, we get 51.75, so that doesn't work. So then we could take 207 divided by 3 squared, which is 9. So 207 divided by 9, that equals 23. So that tells us that over here, 9 times 23 is 207. So we could break 207 down to 9 times 23. So that means we can pull out the perfect square. So the square root of 9 comes out as a 3. The square root of a -1 is I. And then you're left with the 23 underneath the square root. And of course, this is still divided by the 9. All right, then from here, we want to actually divide each one by 9. So we could take 3 divided by 9 plus or minus 3i square root of 23 divided by 9. And 3 over 9, that reduces to 1/3. And then again, 3 over 9 here reduces to 1/3, which would be I square root of 23 over 3. So once again, if you notice here, we have the a plus bi. And also you'll notice that we have plus or minus. Your complex zeros again occur in these conjugate pairs. Remember, if you have one complex zero, you will always have another one that is its conjugate pair. Now notice here you see 1/3 plus or minus I squared of 23 over 3. you may see this answer written as 1/3 plus or minus, let's say, the square root of 23 over 3, and the I may be written over here on the outside. Once again, anytime that I'm writing an imaginary part with a square root, I always like to put the I in front of it instead of on the outside. But keep in mind on your quizzes or on your test with the multiple choice answer, this I may be written instead of on the front of the square root, it may be written on the outside. So keep in mind as you find the complex zeros, realize that you're going to always have two of them and they're going to occur as conjugate pairs. Now, once again, with this example, if you were to graph this equation, if we were to graph this in the calculator, and you're going to have to probably make your screen go from -10 to 20 on the y-axis and -10 to 10 on the x, and your graph is going to look something similar to this. You're going to have a parabola up here at the top, and you'll notice once again, it never crosses the x-axis. So we do not have any real zeros. We're only going to have the two complex zeros. And what I'm not doing is, for example, if you were to take, if we go back up to the first example, if you were to take these two answers, the -3 plus I, if you were to take that and plug it back in up here for x, if you took the -3 plus I, if you take that and substitute that in here, you square it, and then you multiply that number by 6 and add 10, you're going to end up with 0 as your answer.